Hi everybody, so today we're going to talk about exponential decay functions. This time our situation is that we have the amount of medication in a patient's bloodstream decreases exponentially from the time the medication is administered. A patient is given 1,000 milligrams of a particular medication, and the amount of medication remaining in the patient's bloodstream decreases by a factor of 7/10 each hour after the medication has been administered. So the important information that we want to remember is that they were given 1,000 milligrams to start with, and that it decreases by a factor of 7/10 each hour. Okay. Just for the purposes of being able to do the multiplying a little easier, we're going to put this in the calculator so to be able to do that a little bit easier. 7/10 is a nice decimal. It's a terminating decimal, so it's actually 0.7. And that's what we're going to use in as we're finding values for our table and for our equation. Okay. So let's start out with the table. We're going to start with the time since administration. The time since this patient's taken the medicine. We're going to do a process column. Oh, the time is in hours. Okay. And then we're going to do our amount in the bloodstream. So, in bloodstream. All right. So let's start with our time in hours. I'm going to put this one over here. Okay. So when this patient is first given the medication, that would be 0 hours. Okay. If they're just being given the medication, then 0 time has passed, 0 hours have passed. So we're at 1,000 milligrams. Okay. After 1 hour, 1,000 times 0.7 or 700 milligrams. Okay. Well, because this is an exponential decay function, what's going to happen is every time another hour has passed, if we want to figure out how much medication is still in the bloodstream, we're going to multiply by 0.7 again. Okay. So 2 hours, we'll multiply by 0.7 again. And we have 490 milligrams left in the system. I'm sure you can guess after a while it's going to get kind of tedious writing out 0.7, 0.7, 0.7, 0.7 every time we multiply again. So the quick way to do that is instead of writing it out and putting these times 0.7s on there, we can just write it as an exponent. So 0.7 to the second power. After 1 hour is 0.7 to the first power. And just for uniformity's sake, if we wanted to show our initial value on there using the 0.7, it would be 0.7 to the 0 power. All right. Oops, sorry about that. So 3 hours later, after administration, we can do 1,000 times 0.7 to the third power. Okay. At this point, there's 343 milligrams of medication left in the system. After 4 hours, 1,000 times 0.7 to the fourth power, and we have 240.1 milligrams left in the system. And after 5 hours, 1,000 times 0.7 to the fifth power, we have 168.07 milligrams of medication left in the bloodstream. Okay. Don't move that. Let's move this over here. I just want to move this over a little bit. And let's put this in a graph. Let's look at what it looks like in a graph format. Okay. I'm going to count by, we'll go ahead and count by hundreds. So I'm going to start at 1,000. And I'm going to skip a line. So really every line is 50, but I'm only going to write down every other line. So there's 900 and 800, 700, 600, 500, 400, 300, 200, and 100. And then here is our x-axis. Okay, I'm going to try to do this line as straight as I can. Whew. All right. Let's try this again. All right. Kind of clean up my line a little bit. This section is kind of squirrely. All right. And this is the amount left in the bloodstream in milligrams. Okay. Down here, we're going to do our time in hours. So 2, 3. I don't need the tick marks. I just need the numbers 3, 4, 5, 6, and 7. Okay, and this is the time since administration in hours. I'm going to move this up just a little bit. Move it up some. All right. Okay, so at 0 hours, we are at 1,000 milligrams. So we're way up here. After 1 hour, we're at 700 milligrams. After 2 hours, we're at 490. So here's 2 hours. 490 is going to be kind of up here close to the 500. 343. Well, here's 300. That line's going to be 350. So we're kind of right below that. 240. Okay, so there's 50. We're going to be a little lower. All right. 5 hours, 168. So here's 150. We're going to be kind of above that. Those are the only points we have, but it's enough that we can connect them and look at the start of our exponential function here. Let's see if I can. We're trying to connect our points. It probably would have been easy. Okay. Let me try that one more time. We're going to try to connect these points a little bit better. But my pen keeps wanting to go down my x-axis instead of to my points. Okay, that's better. It's not perfect, but it's better. And it's a sketch. We're not looking for it to be a perfect graph right now, and that's fine. Okay. So here's our prediction. Here's our predictor model. We can use a table or the graph just to kind of make guesses as to where we think that amount might be after a certain amount of time. For instance, if we want to predict the amount after at 3.5 hours. Okay, hours. All right. So if we want to predict the amount at 3.5 hours, we've got a couple of places we can look. We can look at our table. 3.5 hours would be halfway between 3 and 5, or sorry, 3 and 4 be 3.5. And if we kind of look 343 to 240, and if we kind of wanted to just estimate maybe about 290-ish. I'm not going to write it in there yet until we have an actual value, but we kind of estimate about 290-ish. Another way we could look at it is go to 3.5 on the graph. And if we go up, we're about right here. You know what, on the graph, that puts us at about 260, 270-ish, somewhere around there. Okay. So yeah, anywhere we can even do a range that anywhere between 270 and 290. You know what, I'm gonna split the difference between the two estimates and say about 280. Okay, 280 milligrams. And this is just an estimate based on the table and the graph. Okay. Now, if we want to know an exact amount, we can write an equation. Okay. So our equation that we could write, just based on our process pattern here, would be 1,000 times 0.7 to the t. Okay, we'll call it t for time in hours, and we're going to say A. So the amount A of medication in the bloodstream with respect to t time, okay, our equation is going to be 1,000 times 0.7 to the t power. Okay. Now, if I actually want to put this in the calculator, I could do that. Put my calculator over. We could do 1,000 times 0.7. And the calculator, we have to do it to the x power. Oh, I forgot my parentheses. Here we go. On the calculator, because we're going to put this into our y equals, we're going to do it to the x power because it's only an xy graph. Because we're looking at a specific point, we're going to go ahead and do times 3.5. Okay. And when we do that, we get 286.97. So our estimate was pretty decently close. 286.97. Okay. I'm trying to, guys, I apologize for the zooming in and out. My tablet is, I'm hitting something on my tablet to make it zoom in and out, and I'm not sure what it is. So bear with me, please. All right. So the actual amount based on our equation is 286.97 milligrams. Okay. Now I have actual in quotes there because remember, this equation is still a predictor. It's, you know, we don't know for sure that's going to be the exact amount, but that's on average what it would be. Okay. Okay. Now, what if we wanted to predict how long it would take to be out of this system? Okay. Predict how long until the medication is completely out of the system. Okay, so completely out of the bloodstream. Well, here's where we have to remember that exponential functions have an asymptote. Okay, we talked about this in our introduction to exponential functions. There is an asymptote at this x-axis. Okay. So no matter what happens with our equation, we can continue this curve going out, but eventually it's going to get super close to the x-axis, and it's never actually going to touch the x-axis. So if it never touches the x-axis, it's never actually going to be 0. So for this predictor about how long till it's out of the bloodstream, really what we're wanting to predict is how long until it's not traceable, okay, till they can do a blood test and not find this medication in the bloodstream. Okay, it doesn't mean it's completely gone. It just means that it's at such a low amount that it's undetectable. Okay, for that, we're gonna go back over to the calculator because it's easier to show you this, to show it visually. So we're gonna do our 1000 times 0.7 to the x power. We're gonna go look at our table. Okay, so here are our values so far at 3.5. It's not on here because it's only counting whole numbers for our x-axis. But we see it went down 1,000 to 700 to 490 to 343. And if we just keep going down, you notice it's continuing to get smaller and smaller. And at 20 hours, now it's actually below 1 milligram. At 22 hours, it's below 0.5 milligram. Okay, it's starting to add more zeros between the decimal and the non-zero numbers. And at a certain point, it changes it into scientific notation. That's what that e to the -4 power means. It means that it's scientific notation. There's going to be the decimal. We had to move it 4 times to the right. Okay. And as we continue on with this, we're going to see that that negative value there keeps getting bigger and bigger. It just means we're adding more and more zeros between the decimal and the first non-zero digit. So it's getting super small, and at a certain point, it's undetectable. Even the calculator at a certain point is going to go, you know what, it's just 0, because it can't do exponential function or scientific notation that high. So we're going to say that it's never out of the bloodstream. Okay. However, after 20 hours, is it 20 hours? It was at least below 1 milligram. Okay. So we're going to, for our predictor, we are going to say that it is not ever out of the bloodstream, but after 20 hours, it is less than 1 milligram. Less than 1 milligram after 20 hours. Okay. Medications are one of our more common exponential functions that we work with, especially with exponential decay. All right, so let's talk about domain and range. Domain, when we look at the domain of our function here, it's going to start at 0 and it's going to continue. Again, it's never going to be completely out of our system. We can continue putting numbers to infinity, and we will get a value out. It's going to be a super tiny value, but it will get a value out. Okay. So our domain, in this case t, is going to be greater than or equal to 0. It's going to start at 0 and continue getting bigger. Our range, and this time our range is the a to the t, okay, or whatever your y we're using as our y variable. Again, it can never be 0, but we do have an upper limit at 1,000. Okay, so we're going to say that it's less, that 0 is less than our amount, but that amount is less than or equal to 1,000. Okay, we're not putting the or equal to on 0 because, again, it's never actually going to reach 0. It's just going to get super close. Okay. All right. So just to tie this back to a general exponential function, in general, when we have exponential functions, y equals a to the bx, or a times b to the x power, the a value is our initial start value. That is our y-intercept. Okay. The b value is, in this instance, it is our decay factor. We previously talked about growth, exponential growth equation, and the b was our growth factor. Okay, so that b value is just whatever we're multiplying by each time. In this case, it is a decay factor. As a decay factor, our b can never be 0. Okay, even as a growth factor, it's never going to be 0. We never want our b to be 0, or our a. Our a can never be 0. If either of them are 0, then our function is just 0. So just those caveats, neither of them are ever going to be 0. As a decay factor, though, our b is going to be between 0 and 1. Okay, it's never going to be 1, but it will be between 0 and 1. Okay, it's just not actually 0 or 1. All right, so when we bring it back to our equation from up above, our a with respect to t for 1,000 times 0.7 to the t power. This 1,000 is our initial value. That's our starting value. Okay. That's how many milligrams we started with when we took the medication, or the patient took the medication. Okay. And this 0.7 is our decay factor. Okay. Now, later we're going to talk about how there's a difference between a decay factor and a decay rate. Okay. This decay factor is just, that's what I'm multiplying by each time. Okay. So that doesn't mean that it is decreasing at a rate of 70%. It's just, that's our factor. We're multiplying by 70 each time, 0.70. Okay. And of course, t is our time, and a of t is our amount in the bloodstream. Okay. All right, guys, that's all I have for you on exponential decay. If you have any questions, be sure to shoot me a message, and I will talk to you later. Bye.